It's a real pleasure and honor to be invited to speak at tonight's celebration of what is possibly the most important astronomical discovery of the last century. And it's a special honor to be speaking immediately before Bob Wilson, who is one of the people who is directly involved in that discovery. So what we'll be talking about here is what we know about the origin of the universe itself. The classic paper that we are celebrating appeared in the Astrophysical Journal in 1965. You would think that this humongous astronomical discovery would be some humongous paper with loads of graphs and tables and whatever. But this is the whole paper right here. It sits on 3 pages, doesn't even fill the 3 pages. It starts at the bottom of the first page and ends in the middle of the second page. That's it. You probably can't quite read it here, but I've enlarged the title and abstract. The title is also surprisingly innocuous for a great astronomical discovery. If you were skimming over titles, you'd probably not even be attracted to this one. A measurement of excess antenna temperature at 4080 megacycles per second. A really bold title. The abstract is similarly bold. Measurements of the effective zenith noise temperature of the 20-foot horn reflector at Crawford, Hogg and Hunt, 1961, at the Crawford Hill Laboratory, Holmdel, New Jersey, at 4080 megacycles per second, have yielded a value about 3.5 K higher than expected. This excess temperature is, within the limits of our observations, isotropic, unpolarized, and free from seasonal variations over a specified period of time. A possible explanation for the observed excess noise temperature is the one given by Dickey, Peebles, Roll, and Wilkinson in a companion letter in this issue. Well, fortunately, this possible explanation is the one that we now all accept, which is what makes this such a fantastic discovery. This really was the clinching piece of evidence for the Big Bang Theory. Now, I suspect that many of the people in the audience here were born at a time when the so-called steady-state theory had already totally met its demise. So it may be hard to conceive of the idea that the Big Bang Theory was not always the theory that everybody thought was right. But in fact, in 1965, there were 2 competing theories. The Big Bang Theory, which was pretty much enunciated by Alexander Friedman in 1922 and developed further by Georges Lemaitre in 27 and Gamow, Alpher, and Herman in the 40s and 50s. But there was also the steady-state theory, first proposed by Sir James Jeans in 1928, and then elaborated very significantly by Hoyle, Gold, and Bondi in 1948. Now, I don't really know a lot, I confess, about the history and sociology of what was going on in the scientific community at this time. But if you just look at this list of names, notice that on the right there are 4 sirs, 3 sirs, I can't count that well. These were the scientific elite of British scientific establishment in Cambridge, Oxford, and so on. On the left, these names are now pretty famous because they were involved in the invention of the Big Bang Theory. But at the time, I doubt anybody thought that much of them. Alexander Friedman was really an obscure Russian meteorologist who wrote down these equations in 1922. He also, from the point of view of public relations, had the unfortunate situation that by the time he was my age, he had been dead for almost 30 years. I stole that from Tom Lehrer, by the way. But he died at the age of 37, and for scientists, longevity certainly always helps to publicize one's work. Georges Lemaitre was a Belgian Jesuit priest, hardly at the center of the scientific establishment. It was true that he had a PhD from MIT as well in physics, and did in fact significant work here at the CFA as well. But nonetheless, he was by no means the center of the scientific establishment. Gamow was a Russian immigrant, known for drinking a lot of vodka. Again, hardly the real image of all the sirs that are on the other side of the screen there. So certainly, it's a fact that many of the scientific leaders of the time were adherents of this steady-state theory, a theory which held that the universe, as it expanded, continually created new matter so that the density of the universe remained fixed and the universe could be absolutely eternal while expanding all the time. You might think, by the way, that you could rule out a theory like this by looking for matter production and discovering it's not there. But it turns out that it only takes an incredibly small amount of matter production to make this steady-state theory work. It only takes the production of about 2 hydrogen atoms per cubic meter per billion years. So it's awfully hard to detect. So even to this day, we have not ruled out the conceivable possibility that matter could somehow be appearing in the universe at that ridiculously small rate. So, in any case, this discovery of the cosmic background radiation really had no sensible explanation in the context of the steady-state theory, although people tried, of course. And ultimately, it led, I think, the entire scientific community to be convinced that the Big Bang theory is the right theory. So here's the picture of the Big Bang as it was illustrated by the NASA WMAP team. The universe somehow began, presumably in some kind of a quantum process, which initiates the Big Bang. Then there's a very brief period of inflation. Not everybody is convinced that inflation happened, but I am, and they are, so it's pretty good. Then, at about 380,000 years after the Big Bang, was a very important event in terms of our cosmic background radiation, what we're talking about tonight. Until this time, the universe was so hot that it was a plasma. And plasmas are very opaque, very non-transparent to electromagnetic radiation. So the photons that filled the universe right from the beginning didn't go anywhere during this first 380,000 years. Each photon at any given instant would have been traveling at the speed of light, but it would constantly be ricocheting and changing directions, and the net effect would be that the light goes nowhere during that time period. But at 380,000 years after the Big Bang, according to our calculations, the universe finally cooled to the point that it was transparent to electromagnetic radiation. And that means that the light that we now see in the cosmic background radiation, the photons, have been traveling on straight lines since about 380,000 years after the Big Bang. And for that reason, they really give us a picture of what the universe looked like at that time, just as the light traveling from my face to your eyes gives you a picture of what I look like. So that's the magic time. The cosmic background radiation really is a picture of the universe at that time. Then very little happened for a while. Then stars started to form and galaxies. Then later, about 5 or 6 or maybe 7 billion years ago, the universe started accelerating again. And Bob Kirshner will be talking about that. He's one of the discoverers of that rather amazing fact. Okay, how does this Big Bang picture work? The picture is basically the idea that the universe as we know it began some 13, 14 billion years ago. And now we think we even know pretty accurately, 13.82 plus or minus 0.5 billion years, according to the latest estimate by the Planck satellite team. What existed before that, one might ask? Well, who knows? It's often said that time itself began at that instant, and that's certainly a possibility. But I think we really don't know, and there certainly are many other speculations in the scientific community by a number of people, including me, for example. Within about 10 to the minus 35 seconds of this beginning, inflation, we think, began. And what is inflation? Inflation is a theory about what I would like to call the bang of the Big Bang. Whoops. Yeah. What I call the bang of the Big Bang. And by that I mean the force that drove the universe into this humongous expansion that we call the Big Bang and that we're still actually experiencing. The universe is still expanding, largely as a result of that initial push that the universe somehow underwent in its first few instants. I might add that before the possibility of inflation was known, Big Bang theorists really had no explanation at all for the expansion. They just took the expansion as a given. The theory of the Big Bang prior to inflation was really only the theory of the aftermath of a bang. All the matter was already present and already expanding at the time that the scientific description of the Big Bang began. But inflation can explain the bang of the bang, the propulsion, by gravitational repulsion. According to inflation, it's a gravitational effect. Now, you may be surprised to hear that gravity can repel, were accustomed to the idea that gravity attracts. And indeed, in Newtonian gravity, gravity is always purely attractive. Newton would have riled at the idea that gravity could somehow behave repulsively. But inflation depends on what I sometimes like to say is two miraculous features of physics, and one of those is gravitational repulsion, which has been part of physics as we know it since the advent of general relativity. Einstein himself used this option in the form of the cosmological constant to build a model of the universe that was static, with this repulsive force balancing the normal attractive force of gravity, preventing his model universe from collapsing. This did not turn out to be a good model for the universe, but it was an illustration of this repulsive gravity effect. And what's happened since is that modern particle physics suggests fairly clearly that at super high energies, by ordinary standards, there should exist materials that behave the same way, that produce this repulsive gravity. The other miracle which inflation is going to rely on is another peculiar feature of gravity, which is that it turns out that the energy of a gravitational field is not positive, but is actually negative. And this actually has been a feature even in Newtonian mechanics, although nobody made much of a deal of it until more recently. And you'll see in a minute how this plays an important role in inflation. So let me go over the sequence of events that we have in mind when we talk about inflation. Inflation proposes that at least a small patch of this repulsive gravity material, this very high energy material that can turn gravity on its head and make it repulsive, existed in the early universe. It didn't have to fill the early universe as long as there was a small patch of it. And we don't really know at what energy scale inflation really happened at, but a very plausible scale is the scale of what physicists call grand unified theories. And I'll give you numerical examples associated with that scale, although there's significant flexibility if inflation happened at a different scale. But at the grand unified scale, this initial patch could be as small as 10 to the minus 28 centimeters across. Unbelievably small. And since this patch is going to be enlarged fantastically by inflation, the initial density of these patches, or the probability that such a patch forms in any given place, can be incredibly low, because after a little while these patches will take over, even if they're initially incredibly rare. Once one has such a patch, the gravitational repulsion becomes the driving force behind a Big Bang within that patch. The Big Bang would become a local property in inflationary theory. The patch would be driven into exponential expansion, which means that it will double in size and then redouble in the same time and then redouble again in the same amount of time. And this doubling time would be as small as 10 to the minus 38 seconds if we're talking about the scale of these grand unified theories. So the patch would have to expand exponentially by at least a factor of 10 to the 28th power to make this work. But that's easy. It turns out it only takes about 100 doublings to expand to 10 to the 28th power. And it could have expanded much more. It doesn't have to stop then. There's no fine-tuning needed in the amount of expansion. There's just a minimum. And at the end, the region that's destined to become the presently observed universe was still very small, about the size of a marble. But then it keeps coasting bigger and bigger up to the present time, by which time it's large enough to encompass everything that we see. Inflation ends because this repulsive gravity material is fundamentally unstable, so it decays. And when I say it decays, I don't mean it rots. I mean it decays in the same sense that a radioactive material decays. It converts itself into ordinary matter, which is no longer gravitationally repulsive. And the gravitational repulsion turns off. And this ordinary matter rapidly forms a hot soup of ordinary particles, sometimes called a primordial soup. And this is the starting point for the conventional Big Bang theory. Inflation is now over, and it joins very smoothly onto the ideas that Big Bang theorists had before inflation was discussed. Now, a key and very important feature of this whole process is that during the exponential expansion, the density of matter and energy did not thin out. As the region expanded, the density of matter and energy inside the region remained essentially constant. Now, that seems very strange because we all know that there's a principle of physics called the conservation of energy, which says that you can't make energy for nothing. So if we have a region that's filled with energy and expanding with energy of the same density, it means the total energy inside that region is going up and up. It doesn't seem to make any sense. But here is where that negative energy of gravity comes in as an important feature. Because the gravity contributes a negative energy to this whole system, the total energy can remain very, very small and constant, and could in fact, and I would guess very plausibly is, exactly equal to zero. And I have a little picture of what that means if it drives it home better. The total energy of the universe has a large positive contribution of matter and radiation, and that's drawn as black the way my accountant would draw it. And then there's a piece in the red, which is the energy of gravity, which is actually negative, and the total balances out to something very, very small and very possibly zero. So that's how inflation works. I'd like to spend the remaining few minutes here talking about some of the evidence that our universe actually underwent this process called inflation. And I want to point to three pieces of evidence, the first of which is the large-scale uniformity of the universe. The cosmic background radiation is uniform in temperature, we now know, to about 1 part in 100,000, incredibly uniform. Now, since it was released when the universe was about 400,000 years old, this implies that the universe was already incredibly uniform at this magic time of 400,000 or 380,000, I called it earlier, years after the Big Bang. Now, if the universe did not start out completely uniform, and we don't know of any reason why it should, although it might have, we don't really know, but if we don't want to just assume the uniformity, but want to ask, can we invent a physical process that would create the uniformity? In order to do it in this amount of time within conventional cosmology without inflation, you would have to be able to push the energy around at about 100 times the speed of light to be able to even things out on such a large scale so quickly. And that's not possible by any mechanism that we know. But inflation takes care of that in a very simple and, I would say, elegant way. Inflation just builds into our history of the universe a short period of humongous expansion, this accelerated expansion during the period of inflation. That means that if we follow the history of the universe back to before this spurt of expansion caused by inflation, the universe would have been much smaller than it would have been in a model without inflation. And it's at this very early time before inflation that the uniformity of our universe could be created, at a time when the universe was so small that there was plenty of time for the matter in the universe to smooth itself out, just as the air in this room smooths itself out. So the air pressure is the same on all parts of the room, and the temperature is also pretty much the same. So the smoothness occurs early before inflation on a tiny, tiny, tiny scale. Then inflation takes this tiny uniform region and stretches it to become large enough to include everything that we observe. Another important piece of evidence for inflation concerns the mass density of the universe. Astronomers and cosmologists measure the mass density in terms of a quantity called omega, which is the actual mass density divided by something called the critical density, where the critical density is that density which is necessary, according to general relativity, to make the universe geometrically flat. In any case, inflation predicts that this quantity called omega should be 1. The mass density should be equal to the critical density. Now, until about 1998, observations seemed to contradict that royally. Bob Kirshner here was always telling me that omega was 0.2 or 0.3. It was really irritating when I had dinner with him. He needled me the whole time. It was awful. But it turned out, in a sense, we were both right. The latest observation now of, again, coming from the Planck satellite, says that omega is 1.0010 plus or minus 0.0065. Pretty close to 1, just like inflation predicts, which is beautiful. The secret, the difference, is the discovery of a whole new form of matter, the dark energy, which indeed Bob was one of the key people involved in discovering it in the first place. And he will be talking more about that, I am confident. So now this all fits in beautifully with what inflation predicts. And finally, and this will be the last subject I'll talk about, inflation not only explains the large-scale uniformity of the universe, by taking something very small and stretching it. But inflation can also explain the smaller scale non-uniformities, which are so important to astronomy and to our existence. We are living on a lump of matter, the Earth, which is an example of one of these inhomogeneities. These inhomogeneities can be seen on a cosmic scale most clearly through the cosmic background radiation itself, where we now can measure these tiny non-uniformities at the level of 1 part in 100,000. And that, of course, leads to the question of, I can't even see what's on that. What does it say? Zero. Oh, that's why I can't see it. I'll finish real soon. Just one more slide after this. Inflation has an answer to where these non-uniformities may have come from. According to inflation, it comes from quantum fluctuations, the inherent uncertainty of any quantum process. Classically, inflation would just stretch everything out and make it smooth. But when the classical prediction says everything is smooth, the quantum prediction is going to say that in some places the mass density will be a little bit higher than that, and other places will be a little bit lower than that. And that's exactly the kind of ripples that we see in the cosmic background radiation. And inflation, in fact, makes a prediction for what the spectrum of these ripples should look like. And by spectrum, I mean exactly the same thing as you would mean by the spectrum of sound waves. Any sound wave can be broken up into its different wavelengths, and you could talk about how much intensity there is at each wavelength. Astronomers do exactly the same thing to the pattern of energy in the cosmic microwave background. And here's the graph, and the data points are the data points. The green line is a fit to the inflationary models. There are some free parameters, I confess. But as you can see, there's just a beautiful agreement between the data and the form of the theoretical curve, making it look absolutely gorgeous for people who are enthusiasts of inflation. To be a little clear about what's being graphed here, the vertical axis is the intensity of these fluctuations as a function of the angular size on the top horizontal axis. On the bottom horizontal axis is something called the multiple moment, which if you know what it means, fine, but don't worry about it. It really just is another way of talking about the angular scale as shown on the top axis. So the bottom line is that the predictions of inflation seem to be working very well, and one of the most important ingredients in testing these predictions of inflation is indeed the cosmic background radiation, which has proven to be our best tracer of what we can learn about the early history of our universe. Thank you.